Welcome to Chapter 5 of Math 215, and this is where we are going to introduce the idea of random variables and probability distributions. So, in Chapter 4 we talked about a statistical experiment, and here we're just going to change the definition just a little. We're going to say a statistical experiment or observation is any process by which measurements are obtained. So for example, measuring daily rainfall in centimeters, counting the number of eggs in a turtle's nest, measuring the weight in pounds of a baby kangaroo, or counting the number of defective light bulbs in a case of bulbs. So first let's talk about random variables. So we could say a quantitative variable x is a random variable if the value that x takes on in a given experiment or observation is a chance or random outcome. So this is a little bit like what you've seen before. Remember in the good old days in algebra, you'd have this variable x, and it's a variable because depending on the equation it's in, it can take on different values. So in this case, this variable x would have to be 2 to make this equation work, right? Or the solution to this equation is 2. So our variable is going to be a little bit like that, but not the same. So our variable x is a random variable because the value that x takes on is random. So imagine you're approaching a turtle's nest and you're going to count the number of eggs. So before you get there, you don't know what x is going to be. If x represents the number of eggs in a turtle's nest, so x could be, maybe depending on the species of turtle, anywhere from 0 to, let's say, 8. So it's a random variable, though, because we don't know what value it's going to take on before we get to the nest. So that's what we talk about here. So each of these could be represented by x, a random variable. And there are two types of random variables. There are discrete, which is what we talk about in Chapter 5. Discrete random variables are easier to work with, so they're almost always introduced first. And then the other type are continuous random variables. These we'll see in Chapter 6 and really beyond Chapter 6. We look at discrete and continuous random variables, but really the ones that we'll mainly focus on are continuous random variables. We'll see those in Chapter 6, and then they go on. They'll be in all the chapters after Chapter 6. We're discrete, we won't spend as much time on, but we talk about them first because, like I said, they're easier to work with and understand. So once we get these down in Chapter 5, then continuous random variables will be easier to learn about because we'll already know about discrete ones. So for these discrete random variables, we say this: when the random variable can take on only a finite number of values or a countable number of values. Countable just means it's not like it can't take on every value on the real number line between, say, 1 and 2, because there's an infinite number of them and you can't pair them with integers. So for the most part, we wanted to get into this kind of detail about what does it mean to be countable. But basically, when you look at these examples here, what you'll notice is these are going to be integer values, right? They're not going to be weird decimals or fractions. It's going to be like 6 or 5 or 0. It'll be numbers like that. Be a finite number of values. So x could be the number of eggs in a turtle's nest, the number of defective light bulbs in a case of bulbs, the number of students in a randomly chosen class, the number of heads when flipping 3 coins. And you'll notice that we're never going to get 2 1/3. 2 1/3 won't work here. We're going to get just kind of nice integer values. So, and they're going to be finite. None of these are going to be infinity, and they're never going to be some weird decimal. It's just going to be basically integers. So the note here is we are counting things in these examples. The key being counting things, right? We're going 1, 2, 3. We're counting things. We're not getting any kind of strange numbers. These are discrete random variables, nice, easy numbers to work with that we just count. We're counting things in these examples. And this is what we're going to study in Chapter 5. But then beyond that, we have to understand what continuous random variables are. So when the random variable can take on any of the countless number of values in an interval on a number line, we say the variable is a continuous random variable. So daily rainfall in centimeters. Now, unlike the number of turtle eggs in a nest, we could get something like 2.54 centimeters, right? Or we could get something like 3.01794 centimeters. Could get 5 centimeters, 5.0 centimeters. But we can really get, if you think of a number line between 2 and 3, how many numbers on a real number line are between 2 and 3? There's an infinite number of them, right? And we could really get any number in here. We'd only be limited by our measuring tool, right? So a continuous random variable is one that can take on, really in theory, any number of values in this interval. So for daily rainfall in centimeters, an infinite number of values we could get here. Weight in pounds of a baby kangaroo. You guys will not believe this. Do you know how much baby kangaroos weigh? 400 pounds. Can you believe it? I hope you don't believe that I made that up. I completely made it up. They're born in a they live in the pouch, right? So they can't be very heavy, but I don't know. Just trying to throw a dad joke in there to keep you guys on your toes. So the daily weight in pounds of a baby kangaroo. So do you guys agree that you could have 2.1 pounds or 2.31472 pounds, or really, in theory, any infinite number of pounds? Air pressure in a car tire, same thing. You could have maybe 32 psi, 33 psi, or any number in here, limited only by the precision of your measuring tool, right? And then we've got the age of a randomly chosen physics professor. So the weird thing about age, and also weight to a lesser extent. So if somebody says, how old are you? You might say something like 23. And it doesn't mean that right at that instant, 23 years ago exactly, you were born, right? So at the end of this video, after you watch this video, you're going to be a little bit older than you were at the beginning, right? Just a tiny bit older. So if you are really like 23.1, and you've got, if you go out to this crazy level of precision out here, as we sit here, isn't this number just ticking away, just like flying around on a wheel? And then it goes slower and slower as you go. So this is 23 years, and then this is just decimal values that represent how old someone is in years. So the way our book is going to do this, when we see age, they're going to think of age like this. Now in practice, most of the times in research, if you're going to publish results, you'll round age to the nearest integer. But for the book, we're going to consider age and also weight. We're going to consider them as continuous random variables, right? Not discrete. So we'll think of age as something like this, where there are, decimal places over here that are ticking away as time goes on. Okay, so those are continuous random variables. And the note here is we are measuring things on a continuous scale in these examples. So that's the difference between discrete random variables and continuous random variables. So for our first example here, on page 206, problem number 2, so this is in the section 5.1 homework, problem number 2, they want us to determine which of the following are continuous variables and which are discrete variables. So take a second and look at that, and let's see what you come up with. Okay, so hopefully for part A it said speed of an airplane, so hopefully you wrote continuous here. Right, it's continuous, it's speed. When you're in an airplane, you don't go from 401 to 402 without going every speed in between, right? 401 miles an hour to 402 miles an hour. You don't like jump from 401 to 402. You cover every value in between, right? 400 miles per hour, 401 miles per hour. You start here and you go all the way to 401. So it's continuous. Age of college professor chosen at random, again, continuous by the way that we're defining it. And in practice, you may actually make that discrete, but for our definition, we're going to go age as being a continuous variable. Number of books in a college bookstore, that is definitely discrete. We know we're going to have the value there will be an integer. Right, it's not going to be a weird number between 2,500 and 2,501, right? It's not going to be like that. Part D, weight of a football player, chosen at random. Again, for weight, we're going to consider that a continuous variable. And then number of lightning strikes, well, that's the number we could count. That's discrete. Okay, so the reason that we have to know about this is we use different math in each of these situations, depending on whether you have discrete or continuous. And discrete random variables take a lot lower level math to work with, but continuous random variables, there's a lot higher level math that's needed to work with them. So probability distributions are something we're going to spend a lot of time talking about pretty much from here on to the end of the semester. It turns out that both discrete and continuous random variables have probability distributions. And a probability distribution is just an assignment of probabilities to each distinct value of a discrete random variable or to each interval of values of a continuous random variable. So here's the key. There's going to be probabilities assigned to distinct values if you've got a discrete random variable, and they're going to be assigned to interval of values if you have continuous random variable. These discrete values, when you work with them, all you have to be able to do is add numbers. For intervals of values, we really need calculus. Without calculus, we can't do this. Now for us, we're going to use the calculator instead. And before that, people used tables. So initially, calculus was used to come up with a table. But once you have the table, then you don't need to know calculus. But it's a higher level of math when you're working with these continuous random variables. And here's a little note here that I think you're going to know. The sum of all the assigned probabilities of a probability distribution must be 1. It's very closely related to that question about the sum of all the probabilities of all the outcomes in a sample space must be 1. The same sort of idea. So don't let this phrase seem too tricky. It's really not. A probability distribution is just a distribution of probabilities assigned to all the outcomes. And when we see this first one here, you'll see they're not really too bad. But just using this one fact that the sum of all the assigned probabilities of a probability distribution must be 1, with that one fact in mind, let's have you guys try this one. Number 3 on page 206 and see what you come up with. So when you're looking at this one, and we're looking at, well, I'll just draw this out for 3A. We have this would be a good one to talk about anyway, so we can see how this works. So put the probabilities in here. So this is how you read one of these. This is a probability distribution. X represents the outcome. So this experiment has 3 outcomes, 0, 1, or 2. And then this is the probability of each outcome. So as an example, let's say there's some species of turtle that is known to only lay at the most 2 eggs. So if you're approaching that turtle's nest and you're going to count the number of eggs, these are the only choices we're going to get, 0, 1, or 2. So the way we read it is these are the outcomes, and then these are the probabilities of each outcome, which means there's a 25% chance there's going to be, in this case, 0 eggs, 60% chance of being 1 egg, and 15% chance of being 2 eggs. Those are the only possible outcomes on this experiment, so these all have to add up to 1. And if you add these up, they do add up to 1. So the answer to this one, determine if it is a valid probability distribution, yes it is. This one is just fine. Now if you look at the one for part B, let me just change this to part B. Part B is similar, but now we have, this becomes 0.20. Now for part B, this is not going to work because these don't add up to 1 anymore. So for part B, it's not a valid probability distribution because the probabilities add up to more than 1. Okay, so let's take a look at a real one here, not a made-up one. So this example 3 tells us we've got an experiment here. We're going to flip 3 fair coins and count the number of heads. So the sample space here is basically everything that could happen, right? So it could be that the first coin, second coin, and third coin are all heads. Or it could be that maybe the first 2 were heads and the third one was a tail. Or maybe the middle one was a tail or the first one was a tail. But in all of 3 of those cases, we have 2 heads and 1 tail. And then, of course, it could be 3 different ways to get 2 tails and 1 head. And finally, the last one is we get 3 tails. So this is everything that could happen. This is the sample space, right? Sometimes abbreviated with a big S, capital S. These are all the things that can happen. You can get 3 heads. You can get 2 heads and a tail 3 different ways, right? Because this would be like the first coin, the second coin, and the third coin. First coin, second coin, third coin. First, second, and third. You could also get 2 tails and a head, and you could get 3 tails. So this is it. This is the entire sample space, everything that could happen. So we've got a table here, a probability distribution table. Now make a little note here. A table that can only happen with a discrete random variable. Think if you're going to do a continuous random variable like this. So here we have number of heads. What if we wanted to make a continuous random variable for the pressure in pounds per square inch? And you want to make a table here. Where would you start? Would you start at 0? Would you start at, maybe the ones that you use are all around between 32, 35. So maybe you're just going to even start at 30. Well, what's the next number going to be? Is it going to be 30.01? 30.001? Maybe 30.5? I mean, what is your next number going to be, right? So there's an infinite number of numbers between 30 and 31. So with the continuous random variable, you can't make a table. But you can with a discrete, which is what we've got. So with this table, we've got the possible number of heads when you flip 3 fair coins is 0, 1, 2, or 3, and then the probability we would put in here. And looking at this, we've got the way you can get 0 heads. There's only one way right here, right? 1 out of 1, 2, 3, 4, 5, 6, 7, 8. So that probability is 1 out of 8. So here, the way you can get one head is right here, right? There's 3 ways you can get one head. So all of these are one head. This is 0 heads. All of these are 2 heads. And this is 3 heads. So to get one head, there's 3 ways out of 8. So the probability that happens is 3 out of 8. Right? So x is the number of heads, probability of x. So 0, probability of 0. 1 head, the probability of 1 head. 2 heads. And then the probability of 2 heads, well, there's 3 ways that can happen out of 8. So it's 3 out of 8. And then finally, the ways you can get 3 heads, there's only one way to do that. That's 1 out of 8. And if you prefer the decimals, as I know some of you do, some of you still are not too fond of fractions. So either way is fine. Then the question is this a valid probability distribution? Well, if you add these up, 1/8 plus 3/8 plus 3/8 plus 1/8 is 8 over 8 or 1, right? So that means yes, it is. Yes, and the sum of all assigned probabilities is 1. So it is a valid probability distribution. So then it says, what is the probability that you will get one head? And of course, we can just look at the table. Here's the number of heads. 1, it's 3/8. Or for the fraction fans, 0.375. So then here they say, what is the probability you'll get 2 or more heads? Well, 2 or more, that means like 2 heads or 3 heads. So we've got the chapter 4 handout for or, but you don't really need it. They are definitely mutually exclusive because you can't you can't flip 3 coins to get 2 heads and 3 heads, right? So they're mutually exclusive. So we just had to add them together. So if you actually really wanted to use the formula from chapter 4, you would add these 2 probabilities together. Or you can just look at the table and say, well, 2 or 3, it's 3/8 plus 1/8. 3/8 plus 1/8, which is 4/8, or 1/2. Or for the decimal fans, 0.5. Now, I know what you're thinking. You're thinking, well, Kurt, that's great seeing that probability distribution table, but I sure would like to see a probability distribution graph. I know, we get that all the time. So let's take a look over here and see what a graph looks like. So what we'll do with this is we will put the probabilities along here on the vertical axis and the possible outcomes here. So our possible outcomes are just the number of heads. So it's going to be 0 through 3. So we'll put those along here. So we'll have like 0, 1, 2, 3. So we want to make them equally spaced. And essentially we're going to have something that looks like a histogram. In fact, the book will call these a probability histogram. But don't think of it like a frequency histogram like we made in the first chapter. These are different. These are probability distributions. So you can look up here. We're going to have this graph here. What's this thing called? A title, right? We want to label the horizontal axis and the vertical axis. Now, the vertical axis for a probability distribution will always be probability. So we need to make sure that we cover the numbers here has to be big enough to cover the numbers from our table. The largest number we've got in our table is 3/8 or 0.375. So if I were going to use decimals, I'd probably make this 0.4 just because it's easy. For this particular one, yeah, I think I will do that also. You could also use fractions here. It works out pretty nice if you just do 1/8, 2/8, and 3/8, but most of the time you use decimals, so I'll do that. I'll put a 0.4 here. I do that because then it's easy to space the rest of them. And here we want to have probability. Right, so we definitely don't want frequency. When we had a regular histogram, we'd have frequency here. But this is a probability distribution, so we need the probability here. And then we just draw this in. So for 0, it's 0.125, so we need to come up here a little ways. So we're doing it by hand again, so it won't be perfect, but we can make it pretty good. And then these are 0.375 for one, and the next one. So I'll go about here. 0.375. The next one also 0.375. And then finally the third one, 0.125 again. So look what we're doing. We want these to be evenly spaced so the graph looks neat. We still need to say what this is. So I'm going to put down here number of heads. I'm going to put something in red that you see sometimes. You don't need it, but sometimes you'll see people put X here, and if you put X there, then they will typically write P of X here. So you'll see that sometimes. Meaning here's our outcomes of our experiment, the possible outcomes X, here they are, and here's the probability of each of those X's. So I'm just going to note a couple of things here. Put note. We need a title because it's a graph. Also, I'm going to note the bars touch. The bars touch like a histogram. This doesn't, this looks like a number line here, but it's not really a number line. Like 1.5 doesn't really mean anything here, right? This is just more like a bar graph where these are the outcomes. So don't think of it like a traditional number line like there's a 3.2. So bars touch. And basically this is just it's a probability distribution of the possible outcomes. It's the same information that was given in that table, but now we just give it in the form of a graph. So this is a probability distribution graph. Well, it turns out that these probability distributions each have a mean and a standard deviation. And as we saw before, X bar is the mean of a sample, just like little s is the mean of a sample. And mu is the mean of a population, and sigma is the standard deviation of a population. So you've got these two sample statistics and these two population proportions. So what we have been doing up until now is we've pretty much been using data in the book, and we assumed it was always from a sample. But at this point, we're going to be moving and dealing with populations more and more. Okay, so you'll notice it. So the first note here, we can say that we'll normally assume our probability distribution is from a population. So that'll be new. We're finding the mean and standard deviation typically of samples. So now we're going to find it of these discrete probability distributions, which will normally come from the entire population. So the note here is before we were finding the mean and standard deviation of raw data. So, if you're feeling fancy, I'm going to introduce you to a new word. Instead of before, you could say hitherto only if you're feeling fancy. Hitherto, we were finding the mean and standard deviation of raw data. It's kind of an old word. It means up until now. Hitherto. Try to use that in a sentence. See if your friends are impressed. Okay, so before we're doing that, now, I don't really have a fancy word for now. I'm just going to go with now. Now we are finding the mean and standard deviation of a probability distribution. Okay, so before, when we work in the first few chapters of the book, they give us some raw data, a sample of numbers, right? Raw data just means the actual data. And we plug it in the list in the calculator and do one variable stats, and we'd use the sample standard deviation. So now what we're going to do is we're going to find the mean and standard deviation of these distributions. And they have applications, one of which we'll use quite a bit, and one of them we won't really use too much. We just have to be aware of it. The mean of a probability distribution is called the expected value. Of the distribution. This is the one we have some applications for. It finds the average or central point of the distribution. So if you look at this notation, the mean mu means the mean of a population. Now when we're using a probability distribution, you'll see this phrase come in for the mean, expected value. And it's a good phrase, and you'll see why when we do this, but it's basically the value you would expect to get. And then this is something that you'll see a lot, not really in our book, but you see this in other books. This always is referring to the expected value when you see this. And this is the formula for it. Basically, it says take the sum of the outcomes times the probability of that outcome. The sum of x times p of x. And that's how we find the expected value of a distribution using this formula, which is actually much easier to use than it looks. So it seems like maybe it'd be a bit of work, but it's not really too bad. But the key is it's population parameter, so we're working with populations now, and we're finding the expected value, which is just the mean of the probability distribution. And then the other one that we become aware of but we don't do too much with is the standard deviation, which is often represented as a measure of risk. A larger standard deviation implies a greater likelihood that the random variable x is different from the expected value, mu, which makes sense. Remember, standard deviation, think back to when we had Team 1 and Team 2. Team 2 had a large standard deviation, and the basketball players had very different heights, right? Some shorter players and some very tall players. They were kind of spread out all over the place. So if you randomly chose the height of a player on Team 2, there was a greater likelihood that that height would be different from the mean, right? That's basically what it's saying. So the standard deviation, there's a formula here, and I used to always go over this formula, and we do a few of them by hand, but now I don't anymore, just because it's just not a formula that people use by hand too much. But you can see it looks like the standard deviation formula from before, where we take a value, subtract the mean, and square it. But now we multiply by the probability of that value. So I'll show you how to do this using the graphing calculator. And again, this is the one, we don't have really any applications in here for this, but they come up a lot in finance or in investing. But what we'll see expected value, which comes up in insurance all over the place. So we'll look at some examples of that. So we've got our probability distribution from before, and we want to find the expected value. So we've got mu, and I'm going to write this this symbol here, even though you don't see it in our book, but you'll see it pretty much everywhere else when it comes to expected value. And then this is the formula for it. So it's the sum of each x times the probability of x. So it's like this value of x. So remember, x is all of these are the possible outcomes. Then this is the probability of each of those outcomes. So we basically just go x times the probability of x. So we would go 0 times 1/8 plus, because it's a sum, plus, then we go to the next one. The next one is 1 times 3/8. So the sum of 1 times the probability of getting one head, which is 3/8. So 1 times 3/8, then we go right down the line. So basically have this, 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 and we multiply across. So at this point we're here. So we have plus 2 times 3/8, and then finally plus 3 times 1/8. And if you add all these up, we can get, let's see, we get 3/8 plus 6/8 plus 3/8, which is 12/8 or 1.5. So you get 1.5. We don't want to round here. We want to keep this at 1.5. So to see what this is saying, let me give you an easier example. Let's say I'm going to flip a coin twice. So 2 flips. If I'm going to flip a coin twice, and I asked you, how many heads do you think I'll get if I flip a coin twice? Well, I could get 0, 1, or 2, right? Probably most of you would think, well, it's a 50-50 thing, so you probably get 1 head, right? And that is what would happen on average. So if I flip a coin twice, I could get 0, 1, or 2 heads, but 1 head is the most likely. Just like here, the extreme ones are the least likely. So if I were going to give you $100 if you guess correctly, and I'm going to flip a coin twice, it's a fair coin, and I say to you, how many heads do you think I'll get? You should say 1, because that's the most likely choice, right? Out of 2 coin flips. So if I were going to do 4 flips, all right, so this time I'm going to do 4 flips, and I said, how many heads do you think I'll get? You'd probably again say, well, it'll probably be half heads, half tails, so two heads. Now again, I could get anywhere from 0 to 4, but 2 would be the most likely. So here we've got the same thing, but we're going to flip a coin 3 times. And again, the number of heads we would get, the expected value of the number of heads is half that many, right? 1.5. So in these 2 cases, when I said 2 flips, you said the most likely would get 1 head, and here out of 4 flips it'd be most likely to get 2 heads. Well, these were actual numbers that I could get, right? I could get 1 head or 2 heads. Whereas here, if I'm going to flip a coin 3 times, I'm never going to get 1.5 heads. I'm always going to get one of these, right? You can see that I've got more of a higher probability of getting 1 or 2 heads out of flipping coin 3 times than of getting 0 heads or 3 heads, right? So what this number means is, let's say I flipped 3 heads over and over and over. 3 coins, and I count the number of heads. So I keep repeatedly flipping 3 coins and counting the number of heads. I'm going to get 1 head a lot, right? There's a 3/8 chance of that. I'm going to 2 heads a lot. And I'll get 3 heads sometimes and no heads sometimes, right? Meaning all tails. But I'm 3 times more likely to get 1 head than no heads. So this is the long-term average. If I did this over and over and over, flip a coin 3 times, I'm going to get 2 heads a bunch of times, get 1 head. Right, and if I just kept on going forever and ever and ever, well, let's just say I did this a whole bunch of times and then took the average, the mean number. The mean number here would be close to 1.5. And in theory, if I did this forever, the mean would be 1.5. So out of 3 coin flips, on average, you're going to get 1.5 heads. Now, you're never going to get 1.5 heads, but this is the average. That would be the average of all of these numbers if I did this over and over. So the first note is, 1.5 is not an actual value from the table. Okay, and that's okay. It doesn't have to be an actual value on the table. So in this experiment, I'm never going to get 1.5. I'm always going to get one of these, 0, 1, 2, or 3. This is just a long-term average. It's the expected value. If I flip a coin 3 times, I would expect to get, on average, 1.5 heads, right? Half of them heads. 3 coin flips, half heads. 2 coin flips, half of them heads. 4 flips, half of them heads. So it's the same as what we were doing here, but it's just an odd number of flips, so you get a value that's not actually on the table. The other note here is basically speaks to what we were just talking about. We'd say on average, we would expect to get 1.5 heads, 1.5 heads from 3 coin flips. It just means like the long-term average, half heads, half tails. Okay, then you see it says find sigma, the standard deviation of x. Well, this is where I used to do this by hand, but I just haven't been doing that anymore. So what we'll do is we'll go right down here, do the one variable stats command. We want to find the expected value and the standard deviation. So the way we do that is we have to put the actual outcomes in list 1. So we'll put these actual outcomes in list 1, put these probabilities in list 2. And we're still going to do one variable stats, but we have to use it a little differently because now we have to make it look in both of those lists. So let's take a look on the calculator and see how to do this. We go to the calculator and we go to stat and go to edit to get to the list. And we've got some numbers in this first list, so I'm going to go up to the name of the list and hit clear out, or clear down arrow, or clear enter to clear it out. Then in list 1, I'm going to put the possible outcomes, which would be 0, 1, 2, or 3 for the number of heads. And then in list 2, I'll put the probabilities, and I can just put it like 1 divided by 8 for 1/8, and it will calculate. It'll write it as a decimal, so I can put 3 divided by 8 for this one, 3 divided by 8, and then finally 1 divided by 8. So to find the mean and standard deviation of this probability distribution, we can still use one variable stats, but the difference is we have to tell it, by default it's just going to look in list 1. We want it to also look in list 2. So we go to stat, go over to calculate. We want one variable stats, so we hit enter. Now, some of you see this, and some of you just see one variable stats. So if you see this, for those of you who see this, we need to go to frequency list and we need to put list 2. Okay, so if you have the other software, hold on just a second, but if you have this software, let's go to frequency list, and then above number 2, you can see off to the left it says L2. So I need to hit second L2. So I hit the second button right here, second, and then 2, and now it says the frequency list is list 2, so then you you go down here and hit calculate. Now some of you though don't see that. Some of you just see one variable stats. So if you just see one variable stats, you're going to have to tell it L1 comma L2. So if you just see one variable stats, you need to go, before you hit enter, it'll just say one variable stats, and then go second L1, and then hit comma, the comma button right here, and then go second L2. So it will look like this. Let me draw this a second. You have like one variable stats. So with the other software, you'll see something like this, one variable stats. If you just hit enter, it'll run the program, but we don't want to do that. We want to hit L1 comma L2 and then hit enter. And so with this older software, you hit, when you get one variable stats, you hit second, then the number 1, then hit the comma, which is the key above the 7 key, then hit second number 2 to get L2, then hit enter, and then from there we should all get this. You can see it's got the mean, got the sum of the x's, sum of the x squared, which we don't need, and it's got the population standard deviation, which we'll use. And as you guys know from one variable stats, it has other things too, which we don't need. So we just want the mean or expected value, which we already calculated was 1.5, and now we've got the standard deviation of 0.866. So one thing I should also mention, for some of you who had the newer software, we need to clear out that L2 value, or else it will still be there. So here's one more quick video. For those of you who have the newer software, you should do one more thing, just so confusion won't happen later. So I'm just gonna get back, let's go second quit, let's just get back to the home screen. If you have the newer software where it has that the little information that came up where we had to tell it, we punched in a L2. If you have that, then if you go to stat, calculate, and you hit one variable stat, see how this L2 is in there? We need to get that out of there, because otherwise, once you put it in there, it stays in there until we clear it out. So if you have this version where this list comes up, then you should go down here and just hit clear, and then just hit calculate. And this is just nonsense numbers that don't mean anything, but that way, the next time you run one variable stats, you won't have to worry about that L2B in there, because if you don't clear it out, it's going to put it in there every time until you do clear it out. Those of you who have this version of the software don't have to worry about it. This version only looks in list 1 every single time until you tell it. So you just have to do that, clear out L2 if you have the other version of the software. Okay, so when we were done with that program, we could see that what we got here for the standard deviation, we got the same mean as what we got before. We had 1.5. We had a standard deviation was 0.866. Okay, so that's how you use one variable stats when we have the data listed in list 1 and list 2. List 1 we had the actual outcomes, and list 2 had the probability of the outcomes. We're not going to do that really too much at all, but just something to know if it comes up or if you want to do it on the calculator. So here we've got an application of expected value that we can try out. So we've got, in this case, a distributor who makes a profit of $25 on each item received in working condition and loses $4 on each item received in non-working condition. So these are the only two things that can happen. Every time somebody walks in the door, this distributor is going to either make $25 or lose $4. That's it. Those are the only two things that can happen. So it does tell us that each item received has a probability of 0.4 being in working condition, And the question is, what is the distributor's expected profit per item? Well, we've got basically this. I'm going to draw out our probability distribution. So we've got x, and then the probability of x. So we've got x, we've got the probability of x. This is a really simple one. X is either going to be 25 or negative 4. And they tell us that each item received has a probability of 0.4 being in working condition. If it's in working condition, the distributor is going to make $25. So the probability of this happening is 0.4. So what's the probability then of this happening? Well, we know it's got to be 0.6, right? There's a 40% chance that the item received is in working condition, which means there's a 60% chance it's in non-working condition. So this is the probability distribution. Every time someone comes in this door, the distributor is either going to make $25, which is a 40% chance of that, or going to lose $4, and there's a 60% chance of that. All right, so you can think of it as people come in, this distributor is going to buy these parts from them, and maybe you can't tell immediately whether they work or not, so then later on, the distributor finds out, and if they're working, he can sell them on to somebody else, and if not, maybe he has to just get rid of them. You know, maybe he paid $4 or something. It's just a simple example just to get one of these to work. So this one is so easy you wouldn't want to do it on a calculator, but if you did, we put this in list 1 and this in list 2, but it's much easier just to do by hand. So the mean of this distribution, the mean of this probability distribution, or in other words, the expected value, right? I'm just going to write all this down. It means the same thing, expected value. Now he said expected profit, so the expected value is probably going to be positive. If it were negative, it would be expected loss. And then we've got this formula for it, which basically whenever we use one of these, it's just going to be x times the probability of x plus this x times the probability of that x, right? So we do just like before, we have 25 times 0.4 plus negative 4 times 0.6. And if you go through here, realizing this is in terms of money, you will get 7.60. And that is the expected profit per item. Expected profit per item, $7.60. Now remember, there's never going to be a profit of $7.60 on an item. These are the only two choices. But this number comes from a long-term average of 25s and negative 4s with a little bit more negative 4s than 25s, right? 60% of the time it's negative 4. So think if you had some game where you were randomly choosing these two numbers, but with the rule that says 40% of the times it's got to be 25, 60% of the time it's got to be negative 4, and you're just adding these up. So you have negative 4, 25, 25, negative 4, negative 4, 25, negative 4, and you just keep on going. The long-term average down here is going to be 7.60. It's the average of all the 25s and the negative 4s. 60% of the time you get negative 4, 25% of the time you get 40% of the time you get a 25. If you add all those up, long-term average, 7.60. So that's the expected value. It's positive, so it's expected profit. And it's just a simple application of expected value. So this next application has to do with something you've experienced, I'm sure, if you ever bought something from, say, Best Buy. And when you go through the register, they ask you if you'd like to buy the extended warranty. And it seems like just about anything you buy, you can get an extended warranty for, even for things that are pretty low priced. I guess some people are very risk averse, so There must be people who buy extended warranties for just about everything. But what we'll do is we'll talk about how to decide whether or not you should buy the extended warranty by using expected value. So in this case, we've got a TV, and it comes with a 1-year warranty, like most electronics products do come with a 1-year warranty, or many of them. But the salesperson asks you if you'd like to buy an extended warranty that covers all repairs for an additional 3 years. So instead of having the 1-year warranty that comes with the TV, you'd now have a 4-year warranty. And it tells you, you're told that the cost of the extended warranty is $50. And according to Consumer Reports, 10% of TVs like yours require a repair, costing on average $150 in the second, third, or fourth year of ownership. So the question is, should you buy the extended warranty? And what we're going to do is figure out the cost of the warranty, and then you can decide. Different people have, answered this question differently. So usually in class, I'll ask something like, how many of you have been through 4 phones in the last 5 years? And there's always some students who raise their hands. So those students are the students who may want to be interested in extended warranties. So some people just have a habit of going through electronics pretty quickly, especially TVs or phones and things like that, computers. So we're going to come up with a cost, but it's really going to depend on the person. So some people buy the extended warranty every time just for the peace of mind it brings, right? So this question depends on the person, but we're going to figure out the cost. So looking at this situation, we're going to figure out the cost with the warranty and the cost without the warranty. So I'm going to say, let's say the repair cost, I'm going to write repair in parentheses because we might not need a repair. But the repair cost with the warranty. So if you buy the warranty, it's $50 for sure, right? $50. So that's repair cost for the warranty. So maybe you need a repair, maybe not, but either way, it's going to cost you $50, right? No matter what. The cost of the extended warranty is $50, so you're paying $50 with the warranty. Whether your TV needs to be repaired or not, still $50. Okay, the trickier part is this repair cost. And again, I'll just put it in parentheses because maybe we need it to be repaired, maybe not. Without the warranty. Well, now this depends. This one's not as easy. So you could think of it like this. This repair cost without the warranty, well, it could be $0, right? Or it could be $150. So if the TV needs to be repaired, it's going to be $150. If it doesn't need to be repaired, it's $0. So we have to figure out by using the expected value what we would expect to pay. We can do that this way. We can say, well, we've got 2 things that could happen, right? It could be that we're going to pay $150, or it could be we're going to pay $0. So in other words, if our TV breaks, we're going to pay, if we don't have the warranty, so we're figuring out the cost without the warranty. Without the warranty, if the TV breaks, we're out $150. And that will happen 10% of the time, right? 10% of the time. So the probability that we pay $150 is 0.10. So if there's a 10% chance that it will require a repair, that means there's a 90% chance that we won't need a repair. So this is the probability distribution for this situation. So we've got 2 outcomes. We pay $150 or we pay $0. There's a 10% chance we're going to pay $150, 90% chance we're not going to pay anything at all. So what we have to do is figure out the expected cost of this. So we can do that. We can figure out the mean of this, or the expected cost. Remember, the formula is this, which is just the sum of each outcome times its probability. So we basically just multiply these together, multiply these together. Now you can see this is just going to be 0. So when we figure this out, we get 150 times 0.10 plus 0 times 0.90, and that's just going to be $15. So the two numbers we have to look at are these two numbers. We've got $50 and $15. So these are the numbers you have to compare. So whenever there's a warranty offered, it's going to work out in favor of the company offering the warranty, because if it didn't, they would go out of business, right? So the company selling the insurance, long term, it has to work out for them. And it does. You can see that it's $15 on average. So if you go without the warranty, you're going to have a long-term average of $15 that you have to pay. So what that means is, if there's thousands of people who go without the warranty, thousands of people, well, 10% of them are going to have to pay $150. 90% of them are going to pay $0. So the long-term average is 15. It's the long-term average of a bunch of zeros with a scattering of 150s, right? So 90% of the people who go without the warranty aren't going to pay anything, but 10% of the people will pay $150. It's just random. So this is the long-term average. So whenever you're in this situation for real and you're asked to buy a warranty, there's two numbers you need to compare. You need to compare the warranty cost with these two numbers multiplied together. You want to compare the warranty cost with the average repair times the probability of the repair. And sometimes this is not as easy to find. You need to know, like, what's the chance that this thing's going to need to be repaired and how much is the average repair. If you multiply those two together and compare this. Now, this number will always be bigger. Otherwise, like I said, the company would go out of business. So you're paying for the peace of mind when you buy a warranty. That's basically what you're paying for. Peace of mind, you know that if something breaks, you can get it replaced. So this is in any of these situations, if you know these two pieces of information, you want to compare that to the cost of the warranty and then make your decision. Like, is that close enough where it's worth it or not? Some people are going to reject this extended warranty every time just because it's, they're pretty good taking care of things. They haven't had any bad things happen or any real bad luck happen. But it's just a personal preference. So, but this is how you figure it out. And then from that point, it's up to you. So one more that I want us to take a look at is one from the book. It's number 18. And this is one of my favorite problems actually in here, because this problem is fairly realistic, simplified somewhat, but it gives you an idea of what actuaries do. And typically in class, I pass around this flyer from the U.S. Bureau of Labor Statistics that introduces the field of actuaries, because a lot of students have never heard of them. But actuaries basically work for mostly insurance companies, but also they really can work for anywhere where you have to make predictions about risk or risk and reward. So it could be like financial companies also. But they look at, for number 18, this is on 5.1, what an actuary would do is look at a life table and try to figure out how much an insurance company should charge a client for life insurance based on what the payout is and the probability that the person will live or die in an individual year. And it sounds like it'd be kind of depressing, but for some reason, apparently it's not. Because actuaries, whenever there's a survey that comes out, every few years about job satisfaction, actuaries are always high on the list. It's a low stress, high paying job, and if you kind of like statistics, don't mind working with computers, that's something you may want to take a look at. So I'm going to post a link somewhere. I'll either email it or put it on an announcement. Somehow I'll get the link to you so you can check it out, or you can just Google it. Just Google this. Just see what an actuary does. Some of you may be interested in it. It's a very good profession to get into. So, all right, to get a little taste of what they do, we've got problem number 18 here. And this one, you have to look at the table on this one. So make sure you're looking at problem number 18. And we've got this Sarah who is, she's going to take out a $50,000 term life insurance policy until she's 65. And they give the probability of death in a given year. So they've got a little life table there. So if you look at the table, it gives her age. It's a probability distribution. It gives her age, 60 to 64, and it gives a probability of death at this age. So if you look at the numbers there, I'll just sketch this one down. So it's got like X, which is the age. And then it's got a probability of death at this age. So something like this. And then she's 60 is right here, and there's 0.00756. So you've got 61 here, 0.00825, and then so forth it goes down to 64. So what you'll notice though when you look at these is the numbers go up, which makes sense, right? So when this person is 60 years old, this is the probability of death based on the they get the information from the Statistical Abstract of the United States. So as the person ages, the probability of death goes up as we would expect. So the way this policy works is, so this Sarah is going to take out what's called a $50,000 term life insurance policy. So there's term, and just kind of a simplified version of this, but there's term life and there's whole life. But whole life is more of an investment product, where term life is, it's an investment product where you get some money back. It's, there's interest involved. Where term life works like this. So she's got this $50,000 policy. So from the time she's 60 until she turns 65, if she dies during that time, her family will get this $50,000 to, for funeral expenses or paying off bills or whatever. So if she dies during that 5-year period, her family's going to get $50,000. If she lives, then she gets nothing at the end. So she turns 65 and she doesn't get any money back. And then if she wanted to, she could buy a new policy for the next 5 years. So she's going to pay the insurance company less than this, of course, less than $50,000 for this policy. So from the insurance company's perspective, they need to figure out how much they should charge her based on the probability of death and based on this $50,000 policy that if she dies, they're going to have to pay this out. So because the probability of death is so low here over this 5-year period, she's probably going to live. But if they have thousands of clients just like her, just think of this happening thousands of times. Occasionally somebody will die and their family will have to be paid the $50,000. So This is what actuaries get paid to do, to come up with the cost the insurance company should charge Sarah for this $50,000 policy. And they have to find the cost where the insurance company will still be profitable and be allowed to survive, but also it can't be too high so that Sarah will go to a competitor. So that's what they get paid to do. So let's just take a look at this one and see how this works. So part A says, what is the probability that Sarah will die in her 60th year? And that's right here. This right here is the probability that she'll die in her 60th year. So 0.00756, which means it's not likely, right? It says she's in reasonably good health, so low probability that she'll die this year, but there is a chance, right? 0.00756. So if there are thousands of clients just like her, some of them will just be unlucky, right? Some people will beat the odds, so to say, and actually die that year. But this is to figure out this individual amount. So the probability that she dies in her 60th year is this. Then it says, using this probability and the $50,000 death benefit, what is the expected cost to Big Rock Insurance? So I'm going to show you a long way to do this just to make it kind of relate to the problem we just did. Okay, so I'm gonna write this down like this. So just to make it, I think it'll maybe make it a little more clear what they're asking here. So we could think of it as two ways. As far as the insurance company is concerned, we could say the insurance company in her 60th year has two outcomes. They could have to pay her family $50,000, and this is the probability that happens, or they could pay them $0. It's one or the other. So the probability here is just the probability that she lives, which is going to be 1 minus this, right? So if I go 1, take away this, I get 0.99244, right? Because if this is our probability distribution, these are the two outcomes, and there's only two, we know this has to add up to 1. So if I add these together, I get 1. So then it's a little bit like that, the example 6 where we did the price of the warranty, where we multiplied these together. So you could find the mean of this, or the expected value, by multiplying these together and these together, just like we always do, right, from this formula. And if you do that, you can see when you multiply these two together, you're going to get a number, and this is just going to be 0, just like before, so it doesn't really matter here. So we multiply 50,000 times 0.00756, and I could say plus 0 times 0.99244, but it's just going to be 0, so it doesn't really matter. So when we do that, what we will end up getting is $378. So what this means is, if the insurance company does this over and over and over, so let's say they have thousands of clients just like her with the same probability of death and the same payout. So at the end of the year, most of these clients are going to get no money, right? There's over 99% chance that the person will live, and so the insurance company will pay out $0. But if there's thousands of clients, some of them will die, right? So this expected value, this 378, this number comes from long-term average. Think of it like this. At the end of the year, the insurance company looks and says, okay, who did we have to pay out? And they look down the list, and it's based on this, right? The people just like her age, and they have a lot more than age. They will sometimes take blood tests. They will call your doctors. So these numbers they spend a lot of time coming up with these numbers. If you ever get life insurance, you'll know that you're going to get a pretty thorough background investigation into your health. So based on these numbers, at the end of the year, most of these clients are going to live. So just think at the end of the year, they're going to say, okay, we paid out $0, $0, $0. There's going to be thousands of these, but occasionally there's a $50,000 payout. And then zero, a bunch more zeros, and a 50,000, and tons of zeros. And you take the average of all those numbers, the average is 378. That's what this is saying. This is the expected value. The expected value is the amount the insurance company should expect to pay out each year for a customer just like this. Now, they're never going to pay out $378, right? They're going to mostly pay out $0 because most of their clients will live, but occasionally a client will die, so they'll get $50,000. And the average of these just tons of zeros and an occasional $50,000, the average of all those numbers is 378. So that's what we're finding. So for part A, it says, what is the probability that Sarah will die in her 60th year? This is it. Using this probability and the $50,000 death benefit, what is the expected cost? All we have to do is multiply these two numbers together. That's the expected cost, 378. Okay, so let me get this set up for part B and then have you guys see what you come up with. So what you want to do is repeat what we just did right here. Mainly we're interested in finding this 378, but we want to find it for these years. So just look on the table there, and you need to multiply this probability of death by the cost to the insurance company if they do die, which is $50,000. So for this 61, I'm going to multiply 0.00825 times 50,000. And when you do that, you should get $412.50. So take a minute here and just go through the rest of the table, multiply each probability by 50,000, and let's put them down here. Okay, so hopefully you did that and you're not just waiting for me. 448, 482.50. There's one just like this in the homework, number 17. Make sure you take a look at that one. There's always, almost always a problem like this that shows up on a test or a quiz, because it's just such a good application problem in my opinion. So what we've got then are the numbers. So this is the expected cost to the insurance company in her 60th year, 61, 62, 63, and 64. You can see it goes up every time because as somebody gets older, their probability of death gets higher, right? Which is just what we know just from living, right? So then it says, what would be the total expected cost of Big Rock Insurance Company over the years 60 through 64? So now they're saying for all of these. Okay, so for part B, if you add all of those up, the total cost is going to be $2238.50. Okay, so this is what this means. Here's the significance of this number. This is the break-even point for the insurance company. So if they're going to offer a client a $50,000 term life insurance policy, and the client's life table is this table right here, they're going to have to expect to pay out this much over the year. Again, they're never going to pay out this much. Most of the time they're going to pay out $0, but occasionally they're going to pay out $50,000. But this is the long-term average of that. So this is kind of like the break-even point. If the insurance company charges this person this much money, and they have thousands of clients, and they in the same boat, and they charge all those clients this much money, long term they're going to break even. So since the insurance company needs to be profitable so they can stay in business and keep offering people insurance policies, they need to charge them more than this. This is the long-term average of thousands of zeros with an occasional 50,000. So for part C, it says If Big Rock Insurance wants to make a profit of $700 above the expected total cost paid out for Sarah's death, how much should it charge? Well, it's going to have to charge this plus 700, right, to make a profit, because this is the break-even point. So if I add $700 to that, it looks like they would have to charge $29.38.50. Right, that's what they'd have to charge for Part C to make a profit of $700 above this. And then we've got, let's see, Part D, which says Big Rock Insurance Company charges $5,000. How much profit does it expect to make? Well, to figure that out, we would just take the $5,000 and then subtract off the $22.38.50, which is the break-even point. And if you do that, then the company would expect to make $27.61.50. So questions about profit revolve around the expected cost to the insurance company for the total of all these years. So you got one just like it, number 17. So give it a shot, and of course try the rest of the problems and let me know if you have any questions.